So good morning, everyone here in person, and good evening or good afternoon, wherever you are. I'm David Kruckmeyer. I'm a principal engineer at Ventana Microsystems. I'm the current chair of the RISC-V CMO, our cache management operation task group. My co-author today is Greg Faber. I'll be presenting for both of us today. He's the Chief Development Officer at Ventana and also the chair of the Privileged Architecture ISA Committee. Today I'll be talking to you about the newly added architecture support for non-coherent I/O and non-coherent I/O devices in RISC-V. Before we dive in, here's a short list of the topics we'll cover today. I'll start by describing a few of the common methods for processors and devices to talk to each other. Then we'll discuss memory attributes in RISC-V, and I'll introduce the page-based memory types extension, or, and this is a mouthful, SVPBMT. I only get that right about half the time. Next, we'll talk about cache management and the new instructions added by another tongue twister, ZICBOM. And then I'll illustrate some software-managed coherence, using the new instructions in producer-consumer code examples. There are many models for processors and devices to communicate with each other, and I've listed a few here. The first is to make devices fully cache coherent with respect to processors. In this model, software is relatively simple because caches are invisible, and memory just appears to be memory. Hardware is more complex, however, because the device participates in the hardware cache coherence protocol to some degree, or must proxy through a bridge to the system interconnect. High performance can be achieved since processors can cache data and no software management of buffers is required. The second model simply maps all memory shared with an I/O device as non-cacheable. Again, software is relatively simple because memory actually is memory, and the devices are simple also because they access memory directly. But performance is low because no data may be cached in the system. The final model involves software-managed coherence. As you can imagine, software is relatively complex since now caches are visible to software, and buffers must be explicitly managed by software. With respect to devices. Device hardware remains simple in this model, and devices, again, access memory directly. In addition, performance is higher than the previous model, since processors can now cache copies of data, and management of buffers is only performed when communicating with a device. The choice of device communication model is system-dependent, based on factors such as performance requirements, IP integration requirements, and hardware-software trade-offs. An architecture needs to provide various options to support a range of systems, and the new page-based memory types extension and the cache management operation extensions enable support for the latter two models in RISC-V. Now I'll provide a bit of background on how memory attributes are specified in RISC-V and how the page-based memory types extension modifies them. In the base privilege architecture, memory attributes are properties associated with a physical address and describe the underlying physical memory location. These physical memory attributes, or PMAs, are specified by memory regions and include properties such as the type of region, for instance, I/O or main memory, the memory ordering model for the region, and whether the data in the region may be cached. Other properties may also be defined. The number of PMA regions that can be implemented in hardware is limited by practical considerations, such as cycle time and the number of address decoders and comparators. A typical implementation may track on the order of 10 to 100 PMA regions, and many of these may be hardwired. As a result, PMA regions are typically coarse-grained and fixed. But larger scale general purpose systems, for example, those running Linux, need flexible memory maps to enable dynamic management of attributes for memory regions. The typical solution is to specify memory types in the virtual memory page table entries, allowing software to determine attributes at a page level granularity. Managing page table contents is understood by software, and modern TLB can cache hundreds or thousands of entries in hardware, so leveraging the virtual memory system to achieve these goals makes sense. In that vein, the new SVPBMT extension defines page-based memory types that enable software to override certain PMAs on a per-page basis. A 2-bit PBMT field has been added to the Leaf PTE, and the field may take one of three values: PMA, IO, or NC. When the PBMT field equals PMA, the PTE does not modify the attributes of the PMAs. However, when the PBMT field equals NC, or non-cacheable, the 4K page is designated a main memory region with RISC-V weak memory ordering. The memory locations within the page are also treated as non-cacheable. On the other hand, when the PBMT field equals IO, the 4K page is designated an IO region with channel 0 strong ordering. Again, the memory region is treated as, or the page is treated as non-cacheable. This extension also works in conjunction with a two-stage address translation defined by the hypervisor extension. In particular, the hypervisor can override the PMAs using the G-stage page table entries to control the memory attributes as seen by the guest virtual machine. In addition, the guest can further control the memory attributes via the VS stage page tables. Among the many possible use cases for this capability is the ability to carve out a non-cacheable buffer and in a PMA region that is designated as cacheable main memory. In this case, software designates the corresponding pages as NC, and processors and devices can communicate using non-cacheable memory accesses. A system can therefore implement a single PMA region that covers all of main memory, and software can create alternate memory attributes anywhere within that region as needed. We'll now shift topics and discuss cache management and its relationship to software-managed coherence. In some systems, higher performance can be achieved by caching data in processors and by implementing coherence in software to manage those caches with respect to non-coherent devices. The new ZICBOM extension, where M stands for management, introduces three new instructions to assist in managing caches. These instructions perform the typical operations. So in other words, CBO inval performs an invalidate operation. CBO clean performs a clean operation. And CBO flush, you guessed it, performs a flush operation. But that really consists of a clean operation followed by an invalidate. I'll provide some more information about these instructions and their operations in a couple slides. Note that these instructions work on cache blocks. And not surprisingly, CBO stands for cache block operation. A cache block is a naturally aligned power of 2 range of memory locations. And for now, cache blocks can be considered to be the same as cache lines, though a future extension may make some distinctions there. Of course, caches introduce the possibility of multiple copies of cache blocks, and the system may implement a mechanism, such as hardware cache coherence, in order to keep those copies and the copy in memory consistent from the perspective of software. As a side note, this extension is one of 3 new extensions that operate on cache blocks. The 2 other ones, ZICBO-Z, which is a 0 extension, and ZICBO-P, which is a prefetch extension, are specified in the base cache management operations along with the management extension. The management CBO extension also introduces a framework that defines coherent agents and coherent caches and describes how those fit together. First, an agent is an entity, such as a HART or an I/O device, that accesses a particular memory location with certain memory attributes. Agents may be grouped into sets of coherent agents, and all agents within a set must agree on the memory attributes for that location. The result is that memory accesses from one agent are coherent with respect to memory access from other agents in the set. Keep in mind that this property is based on a physical address or physical memory location, and that different locations may have different sets of coherent agents. Conversely, if an agent doesn't agree on the memory attributes, that agent is non-coherent. Caches are also grouped into a set of coherent caches if they are accessed by the load and store operations performed by the set of coherent agents. These caches may be accessed directly via requests or indirectly via snoops by the load and store operations of the coherent agents. By definition, management CBOs must operate on any and all copies that are present in the set of caches. Note, however, that these CBOs are not sufficient for managing coherence with respect to instruction fetches. This form of software-managed coherence will be defined in a separate future extension, and it requires cache operations that specifically target the caches accessed by instruction fetches. Now, some characteristics of coherent caches are worth mentioning, since caches have both expected and unexpected behavior. In particular, a coherent cache can allocate a copy of a cache block at any time due to speculative execution or hardware prefetching, and not just due to loads and stores. Furthermore, a coherent cache can also deallocate a copy at any time due to an allocation of another cache block, for instance, due to a conflict or a capacity miss. The net effect is that the contents of a given cache can change outside of software's control and without its knowledge. To allocate and deallocate copies of cache blocks, caches perform read and write transfers, which move copies among the caches in memory. Read and write transfers are related to load and store operations, but are not equivalent. For example, a store operation may perform a read transfer to fetch a copy of data. A cache may perform a read transfer to another cache or from another cache or from memory at any time, and a cache may also perform a write transfer from a cache at any time. But crucially, a cache may only perform a write transfer to memory if a coherent agent has performed a store operation to the cache block since the previous write transfer to memory. As a result, a copy of the cache block allocated from memory by a read transfer due to hardware behaviors beyond software control cannot later overwrite data in memory unless software explicitly performs a store operation to the block. Importantly, this restriction avoids a scenario where a cache performs a read transfer from memory, a non-coherent agent then writes memory, and then the cache later transfers the quote-unquote stale data back to memory, overwriting the newly written data. The system abstraction introduced by the management CBO extension is illustrated here, incorporating the concepts I've discussed on the previous slides. In the diagram on the left, hearts are grouped into a set of coherent agents, and a single device acts as a non-coherent agent, shown as NCA. The set of coherent agents accesses memory via the set of coherent caches, while the non-coherent agent accesses memory directly. Because of hardware cache coherence mechanisms, the set of coherent caches behaves collectively like a single shared cache. However, as shown in the diagram on the right, the set of coherent caches may be implemented hierarchically with various levels of private caches and shared caches interspersed between the hearts and memory. This is simply one example, and many, many other implementations are possible. At present, the management CPO extension does not extend the memory hierarchy between these two levels of caches and memory, although future extensions may add more levels. Now we're getting into the meat here. Now we'll discuss how software uses management CPO instructions to implement coherence. In short, these instructions manage the set of coherent caches, so the data values stored by a process or a heart or a coherent agent are visible to a non-coherent agent, and vice versa. First, the CBO clean instruction forces a write transfer to memory if any store operations have been performed since the previous write transfer to memory. Informally, this means that if the state of a cache block is dirty, then memory is updated and the state of the cache block becomes clean. After a clean instruction, a non-coherent agent can read the data values directly from memory. As mentioned before, data are not written to memory if no store operation has been performed since the last write to memory. On the other hand, CBO inval instruction invalidates all copies of data in the set of coherent agents or coherent caches. Again, informally, this means if the state of the cache is valid, the state of the block becomes invalid. After an inval instruction, a coherent agent can load the data values from memory. In this case, however, the data values either come from memory or they come from a cached copy that has been read from memory after the inval instruction. Finally, a CBO flush instruction effectively acts as both a CBO clean and a CBO invalidate, or CBO inval. Notably, a flush instruction may be substituted for either a clean instruction or an inval instruction. This is interesting. Recall that a cache can deallocate a copy of a cache block spontaneously. In the case of a clean instruction, a clean operation followed by a deallocation is indistinguishable from a flush operation. Likewise, in the case of an inval instruction, a deallocation followed by an invalidate operation is also indistinguishable from a flush operation. And so if the deallocations occur collectively across all the coherent caches, the net effect is the same as executing a flush instruction. Despite these behaviors, optimizations using clean and inval remain, though the latter has subtle security issues that fortunately we won't discuss today. The upshot, however, is that a flush instruction is sufficient for use in all cases. Okay, now we'll use the flush instruction to illustrate the communication between a HART and a non-coherent I/O device. In this first example, the HART is a producer and the device is a consumer. The HART belongs to the set of the HART belongs to the set of coherent agents, and the device is a non-coherent agent. We'll assume the device has a memory mapped register that the HART programs with a command to read or write memory, and this register also indicates the completion status of the device read or write. The meaning of the variables that are stored in the HART registers are there on the left. I think I will skip those in the interest of time. The producer code sequence appears on the right. Initially, the HART produces data in T0 and stores the address in S0. So T0 in this case is the data produced by the HART, and it's stored to the address in S0. To ensure that data have been written to memory, the HART then executes a flush instruction, which is ordered with respect to the previous store by overlapping address ordering rules. Next, the HART executes the fence to order the effects of the flush, which ultimately updates memory, with the effects of the command store to the device register, which ultimately initiates a read of memory. The HART stores the read command in T1 to the register address in S1, writing to the device, and the memory is read from the device, which is implicitly ordered after this store. The device is then guaranteed to read the data values written by the HART. Note that this fence is not a completion fence and only guarantees the flush is ordered with respect to the subsequent memory accesses. In particular, the fence does not guarantee the copy in memory has been updated, but does guarantee that any subsequent accesses to the cache block, in this case the device read, will be ordered after the flush. Now we're going to do some fun animation. We'll see an example transaction flow using the producer code sequence here. First, the initial store modifies a cache copy in the set of coherent agents, or coherent caches. Well, I can't get that straight this morning. Next, the HART issues a flush, and that causes a write to memory. Alternatively, if the set of coherent caches performed an update of memory spontaneously, the flush effectively performs no operation. The fence, which is not shown, orders the flush and the command store to the device. And then after processing the command, the device reads the data from memory. In the second example, the HART is now the consumer and the device is now the producer. Again, the variables are shown on the left. The consumer code sequence appears on the right. And the first thing you'll notice is that this example is a bit more involved. This flush ensures that a write transfer of stale data, let's just start with the store. Before storing the write command to the device, the HART must first flush any modified data to memory. This flush ensures that a write transfer of stale data from the set of coherent caches does not later overwrite the newly written data from the device. Note that this step is really only required if the HARTs have write permission and are actually stored to the block. From a coherence perspective, though, the flush conceptually revokes write permission from the HARTs, while the command store conceptually grants write permission to the device. Returning to the sequence, the fence instruction effectively orders the flush with a store to the memory mapped register and ensures that there's no overlapping write permission between the two. As with the producer sequence, the fence only ensures that subsequent memory accesses to the cache block, in this case the memory device write, will be ordered after the flush. Now we'll assume the HART does some useful work while waiting for a completion interrupt from the device. Once the interrupt is received, the HART loads the device status from the memory mapped device register. So that load is compared with a branch, and branching on the device status creates a control flow dependency between the load of the register and the second flush instruction you'll see at the bottom there. That flush instruction effectively invalidates any copies that may have been read from memory, either before or after the device write. And since by convention, hearts are not permitted to store to the cache block after the first flush, only unmodified copies may be present in the caches at this point. Unmodified copies, again, are not allowed to be transferred to memory. So that after the second flush, the heart is guaranteed to read the data values written by the device. Finally, in this example, a fence is not required between the second flush and the load because of overlapping address ordering rules. Again, we'll see a quick illustration here, this time for the consumer code sequence. The first flush is executed. That basically transfers the write data to memory, any previous store data to memory. The heart then performs the command store, which is ordered after the flush by the fence. After processing the command, the device writes to memory and signals an interrupt. Once the interrupt is received, the heart reads the device status from the memory mapped device register. The heart branches on the device status and orders that with respect to the second flush to invalidate any cache copies that may be present. And then finally, the load is issued and the data are read from memory. Alternatively, a coherent cache may have performed a read after the flush, the second flush, at which point the load data may be returned from a cache copy. So after completing those examples, it's time to wrap up. Today we talked about communication between processors and devices, and we took a brief look at the SVPBNT extension, see, got it right that time, which defines page-based memory types and gives software fine-grained control over memory attributes. Additionally, we dove into the ZICBOM extension, which defines a framework for caches in RISC-V and introduces cache block management operations for supporting software-managed coherence. And finally, we saw how each of these new extensions provide support for non-coherent I/O devices by enabling different models of processor and device communication. You can find additional information at the links here in the GitHub repos. And I'd like to give a shout out and acknowledge the members of both the cache management operation and virtual memory task groups. As Calista highlighted yesterday, this has definitely been a group effort, and everyone deserves credit for the release of these extensions. And with that, I'll thank you, and thank you for your time, and open up to questions.
Please get those questions into the chat if you can. Any questions in the room while we're waiting to see what appears in the chat? I think you answered them all, David.
Yeah,
Go ahead, ask me.
people are being respectful, I think.
So the question was, he noticed that you passed the address on the command. Where do you pass the size of the block? Which command are we talking about here?
Yes,
the
cache
commands?
block.
Okay, all right.
Yes, so the cache block is an implementation-specific property of the system that's discovered through discovery mechanisms in software. And so in the initial CMO extensions, the cache block is fixed across the system. So it's defined as it's defined by the system and can be discovered, and then software needs to operate accordingly.
Okay, we have a question online. Does RISC-V need a completion fence?
A good question. So we definitely had a conversation about that, or multiple conversations about that in the CMO task group. And when it came to the use case we were trying to develop this extension for, which is software managed coherence, we decided that the existing fence, which is an ordering fence, was sufficient for that purpose. There are definitely use cases where a completion fence might be useful, and that's certainly on the list of things that the task group is considering for the future.
Another question, do we need CBO flush instruction for each cache line?
For each cache line that is shared between a processor and an I/O device, yes.
Okay, still looking around here. The next question online, is there any discussion on instruction to zero out a cache line or a cache block?
There is an extension ZICBOZ which is a CBO0, which introduces a CBO0 instruction exactly for that purpose. And it does write zeros to a full cache block. So that was defined in the current set of CMO extensions.
Okay. Last call for final question, and then we'll wrap up, because there's nothing else online. I think we're done then. Thank you very much, David.
Excellent.
Well
Thank you, everyone.